Whoa.
You look so awesome on the live stream.
Thank you. I appreciate it. Oh, I think that's going to be upside down. Okay.
Wait, it's live stream
Yeah.
on
Live streaming now
YouTube?
on YouTube, yep. But it'll save it. It'll save it after.
I'll comment on it right now.
There you
Does it
go.
pop up like the Facebook live streams?
I think so.
This is the coolest teacher I ever met. Like,
Are you gonna? I think it'd be easier if you put it on like far back. Like you could try and put it on that, so you could see the entire thing.
Alright. Did it work? Yeah. Okay.
wait, hold on.
Let's put it here.
You know, does that make sense?
Yes. How about here? But if it's too far back, you won't hear me. So
I think
that should be good, right?
I'll listen to my voice memos that I record on
Alright.
this side and see if I could hear it.
Yeah, if it's too far back, you won't hear.
They have equal.
You got earpods?
I don't have any sugar.
No, you can hear you.
I commented
I,
on it.
when I record from here, I can hear you.
Okay,
Oh, I
let's
see you.
try it. Okay, so it's already streaming. Yeah, and don't worry, it'll save it on YouTube. It'll save it. You can watch it tonight or something. It'll save it automatically on YouTube.
Okay.
So, yeah, this is exam 2. I'm just gonna get these files I need to open here. So that way you can just watch it over and over again and make sure you know all the concepts. This will be cool. All right, start with chapter 6. Does it look okay? Yeah, I think that's fine. All right, let's start with chapter 6. Okay, we were talking about metabolism, chapter 6, metabolism. Again, anything that's in bold, obviously know that well. Remember what I said about studying for the exam? The best way to do it is to go over these concepts on these PowerPoints. If you don't understand something, look it up, study it, and go to tutoring in the science corner. Ask and ask and ask. You don't get tutoring for free at the science corner. And make sure you understand every single concept. That's number 1, right? And then what do? Start on slide 1 and explain it to yourself, right? Use understanding. And then put a check mark. Do you remember my check marks? Put a check mark. Go to slide 2, explain it to yourself. Put a check mark. Go to slide 3, explain it to yourself. Put a check mark, right? And how many check marks are you going to have by the time you're done studying?
A lot.
I didn't tell you?
8, no.
8 to 15. 8 to 15. Try it. That's a lot of studying. That's a lot of hours. I read a lot of your one-page write-ups on how much you studied, and I noticed something. Everyone who studied 1 or 2 days before, or 1 or 2 or 3 hours, didn't do so well. Everyone who studied and studied and studied got an A, right? So, your grade is going to be directly, related to how much you studied, how many check marks you have next to each slide, how much you drilled yourself on these concepts, right? Does that make sense? So, study, your grades will improve, guaranteed, right? Okay, so let's go ahead and start. So metabolism is all of the chemical reactions that are happening inside of an organism. Remember, there's 2 types of metabolism. Anabolic metabolism, you're building things, it requires energy. Catabolic, you're breaking stuff down, it releases energy. These are the different forms of energy. Be familiar with these forms. I might ask what type of energy is related to motion, kinetic, things like that. Thermodynamics, remember the study of energy transformation. Are organisms open systems or closed?
Open
Open systems, very good. know the first law of thermodynamics, what that stands for. What is the first law, right? Energy constant is conserved, right? Yes. Cannot be created nor destroyed. Good. Then the second law of thermodynamics, there's entropy, right? Every time there's an energy transformation, that increases the entropy of the universe, right? That's what we need to know. And why is life not defying that second law of thermodynamics? Remember that? Why does the bear not defy the second law of thermodynamics? If the universe is becoming more disordered, how come the bear is so ordered?
From disorder become organized.
Because you spend energy to become an order.
You're using energy to be ordered, and you're producing
Heat.
heat, which is disorder, and you're also taking those sugars and fats and breaking them down into CO2 and water, which is disorder as well. So the living organism is producing a lot of disorder, and that disorder is paying for the order, right? It's paying for itself to be organized because it's a disorder machine, you see? So because it's causing so much disorder, it is increasing the disorder of the universe, even though it itself is organized, right? It itself is organized. So just remember that. Remember, solids have the least disorder, liquids have more disorder, gases have the most disorder. Spontaneous, remember what that means? It doesn't mean fast, it doesn't mean slow. It could be fast, it could be slow. It means free, right? So it means we'll have negative delta G. It means release energy. It will release energy. It does not require work, right? Very good. Do you remember the concept of capital G, Gibbs, free energy?
Yeah.
Okay. You see this equation?
Yes.
Memorize the equation. Know the equation of Gibbs free energy. Know that equation. Definitely know this equation. Okay. And this equation tells you what? It tells you if it's spontaneous or non-spontaneous. Yes, if a process is going to be spontaneous or it's going to be non-spontaneous. Great.
So if result is negative, that means it's spontaneous,
Yes,
right?
yes. If this is a negative value, it's spontaneous. If this is a positive value, not. If this is zero, equilibrium. That means equilibrium. All right. Now I'm not going to give you numbers to plug in on the exam. No, you're not going to have numbers, but you're going to have concepts. Like for example, how can a reaction that's getting cold? Remember what getting cold means? Absorbing heat, which means positive. How could that possibly be a spontaneous reaction? How could that be a spontaneous reaction?
Positive.
You have to have a
Negative entropy.
What do you think? If I have positive, right? Think about it. If I have a positive number here, how can this be negative? S would have to be a big positive number. Does that make sense?
Yeah.
A big positive number. Does that make sense? So like if this was 10, what if delta S is 100, right? 10 minus 100. You see that? So you have to use logic and reasoning. Like
It's like algebra.
it's not even algebra, it's arithmetic. It's even before algebra. Yeah. It's just math. Like it's very simple. Like so when is a reaction always going to be spontaneous? When it has what?
Delta G.
That would be
Negative delta G.
When is it always going to have a negative delta G?
Positive delta H and
A negative delta
Negative.
H and a
positive
positive delta S. Remember that?
Yeah.
Negative delta H means it's releasing heat, it's getting hot. Positive delta S means more disorder, scattering, more disorder, exploding, right? So do you see that? You cannot have a negative number here and a positive number here and not have a negative delta G. You're going to have a negative delta G, right? Does that make sense? And by the way, if you're looking at me like, how am I supposed to remember all this? You know, it's all right here. It's all, everything I'm saying is right here already, right? This is everything I'm talking about right here. It's already written for you. You don't have to remember what I'm saying, I'm just trying to explain it. See, number one, a reaction that is giving off heat, it has a negative delta H, and if it also has a positive delta S, it's more disordered, it's gonna be spontaneous, guaranteed, right? So those are always spontaneous. If you have the opposite means it's getting cold, right? It's absorbing heat, which means positive delta H, and getting less disorder, negative delta S, that's never spontaneous. That's never spontaneous. It's just math, right? And then the weird ones are when you have negative, or positive. That's when it could go either way, depending on what numbers you're putting, right? Does that make sense? So that's what I want you to know. That's what I want you to know. What types of reactions are always spontaneous? What types of reactions are never spontaneous? And what types of reactions could go either way depending on what you're dealing with, right? Does that make sense? Again, if it's negative, positive, always spontaneous. Positive, negative, never spontaneous. Positive, could go either way. Negative, could go either way, right? Does that make sense? And that's when temperature plays a role. That's when the values play a role. But again, you don't have to plug numbers into this. Remember the equation, and then know, like, you know, what if I ask you, what types of reactions are always spontaneous? There's two ways of answering that, right?
Yes.
Here's one way. Ones that give off heat, and
Less dissolved.
more disorder, right? Give off heat means negative delta H, right? Give off heat means negative delta H. More disorder means positive delta S, positive delta S. Remember that? So again, there's two ways of answering the question. What types of reactions are always spontaneous? Give off heat, more disorder, negative delta H, positive delta S. Those are two ways of answering the same thing. You see what I'm saying? So, and then I could ask, like, what types of reactions are never spontaneous? Well, then you could say, well, the ones that are absorbing heat, getting cold, and release, and getting more ordered, right? More ordered, negative delta H. So that would be a positive delta H, negative delta S. Those are never spontaneous. And then, for example, remember the question I asked? How come there could be a spontaneous process with a positive delta H? You know that one that's getting cold, spontaneously getting cold, that has a positive delta H. How could that possibly be spontaneous if it has a positive here?
We're gonna have more disorder.
You have to have a positive over here, a big positive over here. Yeah, you see what I'm saying? So you have to understand the equation. You don't have to plug in numbers, but you have to use your understanding of this equation, understanding of this, of what Gibbs was trying to tell us to answer those questions, right? So that's good. Okay. So and again, you don't have to stress. It's all right here. It's all written right here, right? So know this for these. Very good. And then remember that. You know, this means high G value, high free energy. This was low G value, low free energy. When you're going from this state to this state, it was a negative change in G, negative delta G. And if you're going the other way, it was a positive delta G. Up here, you have less stability. Down here, you have more stability. And remember the terms exergonic, endergonic. Exergonic means spontaneous. No, not give off heat. You're thinking exothermic. Exothermic means give off heat, whereas exergonic means spontaneous, negative delta G. Exergonic means spontaneous, means negative delta G. Endergonic means non-spontaneous, means positive delta G. And see, these graphs are just doing an overview. These graphs are showing you what happens during an exergonic reaction. You see your G is going from high to low, and you're releasing energy. You have a negative change. And during endergonic, you're going from a low G to a high G. It required energy, so you have a positive delta G. Very good.
So is that similar to anabolic and catabolic?
It is similar. It's similar because a catabolic reaction would look like this. It would probably be a spontaneous or exergonic reaction. And the anabolic reaction would probably look like this. It would require energy to do, and it's a positive delta. Yeah, very good. And remember, equilibrium means there's no work being done. It's easy to achieve in a closed system, but organisms are open systems. We should not reach equilibrium. Organisms shouldn't reach equilibrium, because we're an open system and we're alive until you die, right? And that's when you reach equilibrium. And remember energy coupling, this concept of energy coupling, it's very simple. It just states that you can use the energy that's released from an exergonic reaction and use that energy as the energy required for an endergonic reaction, right? And what is the molecule we use to release that energy usually? ATP. Yeah, because when you hydrolyze the terminal phosphate, it releases a bunch of energy. Why not use that energy as the energy needed for something else, right? For an endergonic reaction, right? Enzyme, yeah.
So remember, exorganics are like the energy exits, right? So it's exorganic. So it's a free energy.
Sure, that's the way you use to remember.
So an endorganic, they enter, energy enters.
That's a good way of learning it. Exergonic, energy is released. Endergonic, energy is used, it is coming in. That's one way of remembering it. That's good. All right, so then we talked about enzymes. Remember, enzymes are catalysts. That means they speed up a reaction without being destroyed, without being consumed by the reaction. They speed up the reaction. Enzymes are usually proteins, and they usually end in ase. Remember peroxidase? Enzyme. Sucrase? Enzyme, right? These are enzymes. They act by lowering the activation energy. What is activation energy? Activation energy is the initial energy needed to start a reaction. Remember I said some reactions happen fast, some happen slow. It depends on the activation energy. If the activation energy is high, it's going to happen slow. If it's slow, it's going to happen faster. So what do enzymes do? Enzymes lower the activation energy. That's what they do. And how do they do it? Hold on, let's go to this room. They do it these 4 ways. So you should know the 4 ways. These are the 4 ways that enzymes actually act to lower the activation energy. These are the 4 ways enzymes lower the activation energy. Remember this example here? This was an example of the second way, bending the substrate's bonds. See? You bend those bonds, the water can attack easier. You've just hydrolyzed, you've sped up the reaction. That's an example of lowering the activation energy. And then remember we talked about the enzyme. We talked about the substrate. The substrate is the thing the enzyme binds to and acts on, right? This is the active site. That's the site where the substrate binds to the enzyme. Okay. Then we talked about, we looked at this in lab today. pH and temperature and all these other factors, they affect how fast the enzyme works, because if you start going too high in temperature, too low in pH, you start messing with factors, you could denature the protein, right? You denature the protein, it lost its 3-dimensional shape. Remember, proteins don't renature, and now that's why you have the flat line, right? That's why you have the flat line, okay? And every enzyme has its own optimal pH and its own optimal temperature. And then we talked about cofactors. Remember, these are enzyme helpers. And you can have inorganic cofactors and organic cofactors. Remember that? Yeah, the inorganic cofactors are the minerals. They're called cofactors. But the organic cofactors, they're usually called vitamins. And here's the thing that you should know. They're called coenzymes, right? So this is what you need to know. The organic cofactors, the vitamins, they're called coenzymes and cofactors. Whereas the minerals, it's not appropriate to call them coenzymes. They're not coenzymes, right? They're just cofactors. Okay, just remember that. And by the way, you don't need to spend time trying to memorize these different vitamins. These are just here as an example showing you that they're organic, right? So you don't have to sit here and learn the difference between vitamin A and vitamin C. You don't have to learn the difference between any of these. I just wanted you to know that vitamins have carbon inside. Okay, and then we had inhibitors. Inhibitors basically do the opposite of cofactors. They stop. And you guys saw, you guys did inhibitor today,
Yeah.
right? And you guys were like, did we do it right? It looks like a flat line. It's like, you did it, that's exactly right. Because the inhibitor stopped the enzyme. The people who did inhibitor, they went from a nice slope to nothing, right? And that shows you that the inhibitor actually inhibited. It stopped, because that hydroxylamine inhibitor, it looks like hydrogen peroxide, and it's a competitive inhibitor. So it's going to block the function. Right? So anyway, inhibitors are substances that bind to enzymes and stop them from working. Okay, and the I say cooperative, I mean competitive inhibitor. It binds to the active site. Hydroxylamine is an example, right? Binds to the active site, stops the reaction from happening. Non-competitive binds somewhere other. And how does that work? It works by allosteric regulation. Allosteric regulation. You should know what that means. Allosteric regulation means when a molecule binds to a protein or enzyme at one site and has an effect at a different site. Yeah, and see that's what this is doing. It's binding to this site and having an effect on that site. You see, that's allosteric regulation. Right. Very good. And remember, the last thing we talked about in this chapter was feedback inhibition. This is when there is a metabolic process, right? And the product of this process is the inhibitor for this process. The product of this process is the inhibitor for this very process. Why do you want to do this? So you don't make too much of this and you don't waste all of this. That's why.
But you still need those.
Because you still need that, right? So anytime your cells have some reaction like this where they don't want to waste all of this, but they need some of this, they're going to use some kind of feedback inhibition. Yeah. And you'll notice, if you don't care about this stuff, then you don't need feedback inhibition. You just make all of it into this, you see? Yeah. And that's it. Any questions about chapter 6? Yes?
So we use feedback inhibition to create the inhibitor, right?
Yeah, well, not just to create inhibitor. It turns out that that product is used for something in the cell,
Right.
but it's also the inhibitor for making itself. So it's two purposes. You're not just trying to make an inhibitor. You're trying to make something that's useful for some reason, but it also serves as the inhibitor for the reaction that made it.
So with the vitamin, you can call that a cofactor or a coenzyme.
Yes, vitamins are both cofactors and coenzymes, whereas a mineral like iron is only a cofactor. So there might be a true-false question or something. Is iron a coenzyme?
It's a
no,
cofactor.
It's a cofactor. It's not a coenzyme.
It's gonna be true or false.
Right? Like, that's a good true-false question.
I bet it's gonna be the same.
Maybe.
So
No,
just
yeah,
only,
it
it was
is.
only no question.
And I'm telling you guys study these notes over and over again, learn these concepts, learn these concepts, learn these concepts, spend time on it, learn it well. There's no reason you shouldn't do really well on the exams. If you learn these slides, if you learn these concepts really well and go over them and over them and over them, there's no reason you should do poorly on the exams. No reason at all. You should get like an A. Yeah.
Do you have advice for like balancing multiple, like for example, if you have like a job in your personal life or other?
Yeah, it is tough. It is tough. All I can say is like this. So the question was, how do I balance job, personal life, and school, and still put in the effort that's required to go over something a lot and spend the enough requisite amount of time? Here, not don't sleep. Actually, sleep is very important. Sleep is very important. Remember my thing? Sleep more than you work more than you play as much as you can. Right?
Yeah.
Like that's,
Way you learn
I like that. But here's the thing. A diligent student, one who's driven to succeed, and once you start succeeding and start seeing the grades, you'll want to succeed more. You start changing your habits. Instead of finding reasons not to study, or like, oh, I was going to study, but this messed me up, so now I'm just going to do this. A diligent student, what they start doing is they start looking for reasons to study, right? Does that make sense? Like, they're looking for opportunities to study, whereas a non-diligent student might be looking for reasons to not. Right? Does that make sense? It's the same thing with like going to the gym. You know what I mean? Like, if you're fit and you like your fitness and you're doing really good with your fitness, you're looking for reasons to go to the gym. It's like, oh, here's an opportunity. I could quickly go to the gym. You know what I mean? But if someone's not doing so well in their fitness and they don't care as much, they'll be like, oh, it's kind of drizzling, and maybe I'll skip the gym.
It's far away.
You know what I mean? It's this mentality. It's this mentality. It's like, oh, here's an opportunity to study. Here's a chance I could fit some. Oh, you know what? This is my doctor's being late right now. I'm waiting in the patient's office in the waiting room. Well, let me bust out my notes and do my checkmarks. I'm gonna have to wait in line for Subway. Let me do my checkmarks. You know what I mean? And yeah, you don't have a ton of time because you're working and you've got all these things going on. But you could make time, like find opportunities to study. And then with the social life, not forget it, but minimize, just say, hey, I'll see you guys on the weekend. I'll see you guys on the weekend. And not even the whole weekend, like part of Saturday. I'll see you guys Saturday night after I've studied the whole week. You know what I
Or
mean?
make your friends part of the study.
Yes, or make your friends part of the study group, part of the study, and a lot of times you'll help your friends out, you know what I mean? Like, because believe it or not, when I was in my PhD program, I was dating my girlfriend, who's now my wife, right? But so I was dating my girlfriend, and she knew I was a very serious student, right? And even on Friday nights, I might have to study. So I would go to the bookstore and study, and you know what she would do? She would come and sit with me. You know what I mean? And she would sit with me and read a book, at the bookstore. And I would be studying, and we'd have a coffee, and we'd kind of talk, but then I'd study. She was so cool. But then after a while, she said, you know what? I'm coming and sitting down with you anyway, and watching you study. Why don't I study? Because here's the thing. She's a tax accountant. She got her master's in tax, right? So, and she never did her CPA exam. The CPA exam?
Yeah.
That's like the bar exam, but not for lawyers, for certified public accounting, right? Big exam, really tough exam. She took it one time, didn't do so well, and then she said, I'll do it later. So she hadn't really done it, right? But then she said, you know what? I'm sitting with you anyway, and I'm just having coffee and reading a magazine. Why don't I study for this test? And I'm like, yeah, study for the test. You study for your test, I'll study for my PhD. And you know what? She started studying. So we would meet and she started studying. And you know what's funny? She told me later on, she's like, until I met you, I didn't know what studying really meant. And I was like, I'll take that as a compliment. And then she started passing them. There's 4 exams, and it's really hard test. I don't know if you guys know about the CPA test. It's a really hard test. It's not like one-day test. It's 4 parts. One day you take one test, and then you study a month, and you take the next test. And then you study a month, and you take the next test. And if you fail any of them, you have to retake that one.
Oh, wow.
Yeah, there's 4 different tests.
Retake for all and only one.
Yeah, you have to, and here's the thing, if you fail one, you have to pass it within a year. So, she had passed 2 and then failed 1, and then she, but she started studying, and next thing you know, she started passing all of them, and she became a CPA, right? And she, and that's the thing, what I'm trying to do is tell you guys, your friends may want to party, but you tell them, hey, I'm studying. If you want to join me and study, like that's cool. Otherwise, I gotta study. And the ones that join you will thank you later.
So you like
They will-
inhibitor.
I was an inhibitor, a fun
Then
inhibitor.
I just want to go party and
I
do
was a
inhibitor.
feedback inhibitor. See, you're making these, but that's the thing. And now, she's a CPA, I'm a PhD, but it's because we sacrificed some fun when we were younger, and now we live well. You know what I mean? And now we can thank ourselves for doing that. You see what I'm saying? So that's what I'm saying. Like, if your friends, your friends may not want to do what you're doing, but you can influence them to change their ways. You know what I mean? And in a good way. But anyway, that's that. Let's keep going with chapter 4 now. Right? Yeah.
But I wonder why you don't marry her and you marry someone.
Yeah, no, we ended up getting married, and now it's really nice. Yeah.
She's a keeper.
Yes.
Very,
Yes, definitely a
not the
keeper.
same point.
Yeah.
Not the same income.
Yeah.
Right.
Same.
That's funny. All right, so let's keep going. Chapter 4. Remember the cell. The cell is the basic unit of life. The cell is the basic unit of life. You can't be simpler than a cell and be alive. Cells come from pre-existing cells. Remember all this stuff?
Yeah.
There are 2 types of cells, prokaryotes, eukaryotes. The prokaryotes are the bacteria and the archaea. Those are the domains. And then the eukaryotes, that domain is the eukarya. And remember, the eukarya includes the creatures, protists, fungi, animals, plants. All of these are eukarya. These are the things that all cells have. You should know these are the things all cells have. All cells have chromosomes. All cells have plasma membrane. All cells have ribosome. All cells have a cytoplasm. Right? And remember this. Prokaryotes, how many chromosomes do they have?
40.
No, prokaryotes. Bacteria.
Just
And
one.
One chromosome, and what shape does it have? It's a
circle,
closed circle. It's still double helix DNA, but it's a closed circle, right? So, and that DNA in the cell is called the nucleoid.
Nucleoid.
Prokaryotes have a nucleoid. Eukaryotes have a nucleus, which means their multiple chromosomes are inside of a double membrane. Like that. Yeah. So good.
Okay, so are mitochondria cells or organelles?
That's a good question. Are mitochondria cells or organelles? Millions of years ago, they were cells. But then once the endosymbiont event happened, now they're considered organelles. Because, you know why? Because they've lost the ability to live on their own. You can't take a mitochondria out now, millions of years later after the endosymbiont event happened. You can't take a mitochondria out of a cell and say, grow now. They can't, because it's lost the ability, over millions of years, it's lost the ability to grow on its own. So it's no longer a real cell.
But there's still DNA.
But it still has DNA, it still is like a zombie cell from before, yeah, it's pretty neat stuff.
Eukaryotic, that's still got the stomach for the carry the genes and the chromosome, right?
Yeah, all cells have a chromosome,
Yeah.
at least one chromosome and ribosome.
So the difference is just about the chromosome that carry the DNA.
Chromosomes
Yeah,
are
inside.
made of DNA. Chromosomes are made of DNA. Yeah, and chromosomes, each chromosome houses thousands of genes. There are thousands of genes, or at least hundreds of genes on each chromosome. Okay, and then prokaryotic cells, remember, prokaryotic cells do not have a nucleus, they do not have membrane-bound organelles, but they do have a membrane that's called the plasma membrane. Remember, all cells have a plasma membrane. And bacteria, only bacteria, not archaea, they have a cell wall, and the cell wall is made of peptidoglycan, right? Okay, so again, you see the prokaryotic cell, you got the nucleoid, you got the cytoplasm, ribosomes, plasma membrane, cell wall. If it's a bacteria, it has a cell wall of peptidoglycan. Then we have, yes?
Can you go back to the slide? Was that like the bacteria, right?
This is a standard bacteria.
Okay, standard bacteria.
Yeah, like, and some bacteria have a flagella,
Yeah.
some don't, you know. But they all have a nucleoid, ribosomes, cytoplasm, right? And a plasma membrane.
Okay.
Eukaryotes have membrane-bound organelles, and the main membrane-bound organelle is the nucleus, right? And remember, the plasma membrane, all cells have a plasma membrane. This membrane, encompasses the entire cell, envelops the cell. This is a typical animal cell. What does an animal cell have that plant cells don't? It's good to know.
Centrioles.
Centrioles. And who remembers what they're made out of?
The tuber.
Microtubules, yeah, you guys got it, microtubules. And they're involved in what? Doing what? What is their job?
They divide,
centrioles?
when they divide, the cell divide.
Separate the DNA.
Separates the
Separate the
chromosomes when the
chromosomes.
cells divide, right, exactly. Very good, you guys are on top of it. I feel like all the scores are gonna go super high this time.
I hope so.
Yeah. Remember, you can do it. It is very, very possible to get an A.
It's different when you understand these and then when you read the test.
No, hopefully not, hopefully not, right? But when you do read the test, just remind yourself, I know this, you know? Just no, it's a big thing. When you're reading the questions on the exam, if you study, just keep reminding yourself, you know, like, I know this, you know? Like, and then just calm down, I say, I know this, and then just calmly, you know, scratch out the ones that are not right, and then, you know, you select the one that's right. Okay, 3 structures plant cells have that animal cells don't.
Central
Cell wall,
Central vacuole and
chloroplast, yeah.
Chloroplast.
Cell wall, central vacuole, chloroplast, yeah. So plant cells, do they not have a plasma membrane?
They do.
They do.
They do.
They do. And plant cells, do they not have a mitochondria?
They do.
They do.
They do. They do have mitochondria. Those are common mistakes. Good. And then, of course, know these parts.
Nucleus.
Right, nuclear envelope is 2 membranes, remember that? The nucleolus, you should know the nucleolus is
Inside
where the
nucleus.
rRNA is made, the rRNA, ribosomal RNA. Nuclear pores. Chromatin means DNA wrapped around protein, right? DNA wrapped around protein is called chromatin. Your chromosomes are made of chromatin, right? DNA wrapped around protein. Here's the thing. Here's a good one. Nuclear lamina, remember this? This is the support for the nucleus. What's that made out of?
The post of the structure of the nucleus.
Protein?
Which one?
As a structure of the nucleus, right?
The code.
It codes the nucleus, it gives structure to the nucleus, but what is it made out of?
Is it micro?
Make the shape of the nucleus.
You're on the right track.
Micro. The second one, the thin one.
No. The third.
The third one? Where's my note?
Wait a minute.
Oh.
Intermediate filaments.
See, I don't know about that.
Nuclear lamina is made of intermediate filaments. You're like, how was I supposed to know that? Let me show you. Look at this.
Got it.
Look. Look.
There you go.
Intermediate filaments make
Oh yeah.
nuclear lamina. The nuclear lamina is intermediate filaments. Okay, the nuclear lamina It's intermediate filaments. That's good to know.
Okay.
Okay, good. And then that's about it from there. Then we talked about ribosomes. Are ribosomes only made out of protein?
No.
No, it's protein and
RNA.
RNA. And the RNA part of the ribosome is called
The
rRNA, which is made in the
Nucleolus.
nucleolus. Remember that?
Nucleolus.
The nucleolus made the RNA part of the ribosome. And the ribosome is part protein, part RNA. The ribosome itself is not just protein, it's part protein, part RNA. And there's two subunits, the large subunit and the small subunit. Remember like hamburger bun, large bun, small bun?
Large bunch.
Mitochondria, chloroplasts. Mitochondria is where ATP is made, right? That's called cellular respiration. Chloroplasts is where sugars are made. That's called photosynthesis. Okay? Remember, this is the evidence. This is the evidence for the endosymbiont theory. Okay, remember, this is the evidence that tells you that this happened, endosymbiont theory. How the mitochondria came to be, how the chloroplasts came to be. So I might ask you, like, what is the evidence for the endosymbiont theory? What is the evidence that shows us that the mitochondria used to be a creature once upon a time? Remember, it has its own DNA. It grows like a bacteria. It has its own ribosomes. Its genes are similar to prokaryotic genes. And then we talked about the mitochondria. You should know the structure of the mitochondria. You should know it has two membranes, outer membrane, inner membrane. The inner membrane has folds. What are the folds called? Cristae. Cristae. And then the space between the two membranes is called intermembrane space. That's the space between the two membranes. What's the fluid in the middle called? Matrix. And then it also has DNA and ribosomes. Good. Then we talked about chloroplasts. And the chloroplasts have three membranes. It's got the outer membrane, the inner membrane, and then it has these stacks of membranes. Remember? Those stacks are called granum. The membrane of the stack is called the thylakoid membrane. Each pancake in the stack is called a thylakoid.
Are these good to are they good to remember? Is granum and
Yes.
stoma and
Yes. It's good to remember. You might get a question like, here's a true-false question. Stacks of thylakoid make a granum, or stacks of granum make a thylakoid. Yeah, the first one was true, the second one is false. See, a stack of thylakoids is a granum.
Yes.
Not a stack of granum is a thylakoid. So if you don't know which one's one pancake, which one's the stack, you're not going to get those questions. Right?
Stack of
Right.
pancake.
One of these is a thylakoid. The whole stack is a granum. Right?
Granum.
So there are questions like that. And then the fluid outside of the stacks is called the stroma. The fluid inside is called the thylakoid space. So you might want to write that because it's not written anywhere. The fluid inside of the pancakes is called the thylakoid space. Very good. And remember, it also has its own DNA. It also has its own ribosomes.
So.
And then we talked about the ER. Rough ER, smooth ER. Remember this. This is actually good to remember. The nuclear envelope is actually connected to the ER. It's called continuous. Continuous. You see? The nuclear membrane is continuous with the ER. What does that mean? They're connected. You should know that. The nuclear envelope is continuous with the ER. It's connected to the ER. And here, you should know the jobs of the smooth ER. I might have a question. All of the following are jobs of the smooth ER, except, and if you don't know the jobs of the smooth ER, you won't know which one's the wrong one, right? These are the jobs of the smooth ER. What does the rough ER do? Protein synthesis, because it has ribosomes.
So is it the smooth ER is connected to the rough ER?
Yeah, but it's just lacking those ribosomes.
So the rough ER transport ribosome?
The rough ER has ribosomes attached, and the ribosomes are making proteins at the rough ER. The ER will then pinch off and transport those proteins in vesicles.
So ER doesn't produce proteins.
The
Ribosomes.
ribosomes at the ER.
ER just here transfers the.
Transfers them.
Yeah.
But if I were to ask what is happening at the rough ER, you could say protein synthesis, because it is happening there. Yeah.
Would it be like a building where
Building.
the ribosomes are?
The ribosomes are building the proteins, but they're building it at the rough ER because they either want to weave those transmembrane proteins into the membrane, or they want to put as they're building the protein, they want to put it into the ER. Yeah, that's why they're doing it. And then the Golgi, remember the Golgi, it has a cis phase and a trans phase. It accepts proteins from the ER at the cis phase, and then it modifies them, and then it ships them off at the trans phase. Remember that? And here's one thing I don't know if we covered, but you should know this. The sacs, you see these sacs?
Yes.
They're called cisternae. Cisternae. Don't confuse it with cristae. Cristae are the folds of the inner membrane of the mitochondria. Cisternae are the sacs of the Golgi. And again, vesicles from the ER attached to the cis phase. So the cis phase accepts proteins, and then it modifies the proteins, and then it transfers it. It exports the proteins, ships them from the trans phase. The cis phase is looking at the ER and the nucleus. The cis phase is looking at the nucleus. The trans phase is looking at the plasma membrane. Good. And then we talked about the lysosome. This one's easy, right? It's an organelle full of hydrolytic enzymes. Hydrolytic enzymes. Then we talked about the 3 types of vacuoles. Just be familiar with the 3 types of vacuoles. Okay? Then we talked about the cytoskeleton. So for each of them, you should know the general shape. Remember, the microtubules are the thickest, microfilaments are the thinnest, and the intermediate are in the middle. For each of them, know the general shape, what protein they're made out of, and what are the jobs. Here are the jobs, right? So, general shape, protein, jobs, right? General shape, protein, jobs. And you should be fine, right? Does that make sense? So, like, for example, centrioles are made of microtubules, and they're involved in chromosome separation, right? Flagella and cilia require microtubules. And by the way, you should know the difference between how the flagella works and how the cilia works. Yeah, the flagella works by just beating back and forth, okay? The cilia is power stroke, stroke, recover. So you should know, flagella beats back and forth like a fish tail. This one, power stroke. The cilia, power stroke. There might be a true-false question on that, right?
Might be.
And then you open it up, you should know it's called the 9+2 arrangement. Inside of the flagella, you have the 9+2 arrangement. 9 doublets, see?
And 2.
With 2 singlets. And then the little motors, the walking legs are called?
Motor proteins.
Motor proteins dying. Those are motor proteins. These are the little red Ys. They're the little walking legs. Yeah,
They make it
they make it beat
with ATP.
with ATP. With the help of ATP, they beat and beat. Okay? Microfilaments, remember, they're in the cortex, which means right under the plasma membrane, you've got the cortex. So whatever the microfilaments are doing, they're just going to change the shape of the cell. The microvilli of your intestines are because of the microfilaments, okay? Your muscles require microfilaments. Pseudopods, you remember like amoeba pseudopods? Microfilaments. Cytoplasmic streaming, microfilaments. I may have questions like, microfilaments are involved with all of the following except, and if you don't know the jobs of the microfilaments, then you don't know which ones except, things like that. And also remember when the cell itself, the cell is dividing into two cells. That pinching, you see this pinching of the membrane, that's called cleavage furrow, and that's also thanks to microfilaments. Microfilaments are involved with the cleavage furrow. That means the animal cell pinching into two cells, this constriction of the membrane, cleavage furrow, right? Microfilaments. Then we talked about the intermediate filament. This was the most boring one. Now here's the thing. Intermediate filaments, are they known for dynamic stuff? You know, dynamic means movement. Are they intermediate known for movement and motility?
No. What is shape?
No. So, you know, I may ask, like, which one of the following microtubules, microfilaments, or intermediate filaments is not known for anything dynamic, any dynamic process?
This one.
This is right. This one's for anchoring and support and structure. Nothing, no like muscles or anything like flagella, cilia, nothing like that, right? It's just, you know, it's just anchoring stuff, supporting stuff, giving structure, right? Does that make sense? And what is the main thing I wanted you to remember about that besides it anchors and supports and doesn't do anything dynamic? It's involved in the nuclear lamina. Nuclear lamina. Yeah, it makes the nuclear lamina, which is the structure of the nucleus. Okay? It's the support. I know you feel like, where's that? Remember, it's here. Intermediate filaments, nuclear lamina. Okay. Good. And then we talked about extracellular matrix. Well, actually, first we talked about extracellular components, right? So look, plants have what extracellular thing? Cell wall, cellulose cell wall. Fungi have chitin, yeah. And then animals, they don't have a cell wall. Animals do not have a cell wall, but they have extracellular matrix, right? And you should know about the extracellular matrix. The main component is collagen fibers. These are protein fibers, collagen. And then you also have proteoglycan complex, which is part sugar, part protein, and that kind of, you know, it's like barbed wire, intertwined. Both of those connect to fibronectin, which connects to the anchor. This is the anchor protein called integrin, and the integrin connects to the microfilaments. So again, here's how it works. Microfilaments attach to the anchor protein. This is a transmembrane protein. Remember what transmembrane means? Spans the whole membrane. You see that? Up and down. The transmembrane protein integrin is the anchor. Then that connects to the little adapter fibronectin, which connects to the cellulose and the proteoglycan complex. So all of it's connected. And that's why it gives you structure and support to the cell. Okay? So, you know, the anchor is called integrin. Right? Cool. And that's it. That's the whole exam. Right? All right, any questions? Now, actually, we have an in-class activity now. Yes, yes. So I will stop the stream. Thank you for watching. Right?